Hello. Now we are going to look at the slopes of lines in some detail. So the slope of a line is how quickly or slowly it goes up or down. And we can describe that more mathematically by saying that the slope, which we usually call little m, so not capital M but little m, is the rise divided by the run. If we run across by a particular amount from left to right, how much do we go up or down? How much do we rise? And we can write this as the change in up and down value, which is y, the change in y divided by the change in x. So this triangle symbol here means delta, and it means the change in something. So the change in y divided by the change in x is just a more mathsy way of saying rise divided by run. And to put it into terms of coordinates, we could look at the y value of the second point minus the y value of the first point. That would give us our change in y, divided by the x value of the second point minus the x value of the first point. And this formula here, m is equal to y2 minus y1 all over x2 minus x1, is on page 18 of our formula tables, of our log tables. Whenever we are viewing a graph and we're looking at the slopes of the lines involved, we always read from left to right. So we start on the left and we read across to the right. So our run across is always from left to right. And we would say that a slope was positive in this context if it rises to the right. So as we read from left to right, is the line going upwards, or as we go to the right, is it going downwards? So here we would say that the slope between A and B in this little line segment here would be positive. It's rising, it goes up as we read to the right, and the slope of our green line L is going to be negative because it is dropping to as we read to the right. So as we go across reading left to right, our green line is going downwards, so we'd say it had a negative slope. It's dropping as we read left to right. Now let's put this formula business into practice with a few examples. Now in terms of notation, we have the slope of a line through AB. Our little line segment here would be little m, so not capital M, but little m, subscript AB. It's important to be able to talk about the slopes of different lines because often we'll have to deal with more than one line at once and therefore more than one slope at once. So being able to clearly label what slope we're talking about, what line we're talking about, is very important. So this is going to mean the slope through the points A and B. So if we take a visual way of doing this to begin with, let's just take A and B. So if we have the point A as our starting point and we're going to the point B, that means we run across 4 boxes on our grid, and we can see that we're counting in ones here. So and we're counting in ones on our y-axis as well. So we run across by 1, 2, 3, 4, and we rise by 1, 2. So our rise over our run would give us 2 over 4, which I know simplifies. I have a common factor of 2 top and bottom, which I can factor out and divide out, which will mean that my slope is 1 over 2. So if I run across by 2, I rise by 1. If I go back to my line for a second, if I run across by 2, I rise by 1, and I get back to my line again. So I can use my grid, my coordinate axis, to allow me to visually figure out what the slopes of lines are. And often that's a really important way to do things. However, we also have formulas that we can use, and we're going to practice doing that now. So if I want to know the slope of the line between A and B, I can use my formula on page 18. So I write down my coordinates. So for my point A, I would be going in the door 10 and up the stairs 12. So my coordinates of A would be at 10, 12, and my coordinates for B would be start at the origin, in the door 14, up the stairs 14 as well. So A is at 10, 12. B is at, I want to give myself a little bit more space than that. B is at 14, 14. So if I write down my slope formula, m is equal to y2 minus y1 all over x2 minus x1. The difference of my y's divided by the difference of my x's, effectively my rise divided by my run, just written out in more formal maths language. Well, how would I use this formula? Well, I have the coordinates, the x and the y, for 2 points. So these are my 2 points, A and B. So what I do when I've written down my coordinates for A, I'm going to write x1, y1. A is going to be my first point, and B is going to be my second point, and that's x2, y2. Doesn't actually matter which you pick as being your first and second point. This formula actually works the same either way. So I've picked my first point, and I have my x1 and my y1 for first x value, first y value, second x value, second y value for my second point B. And I sub into that. I have 14 minus, I should put everything in brackets, 14 for y2 minus 12 for y1 divided by x2 is 14 minus x1 is 10. And when I do that out, I get 2 all over 4, because this is effectively the same logic as what we did here. We found the difference, our change in x divided by our change in y, or other way around. We found our change in x divided into our change in y. And when we simplify that, we get a half. So we can see that the formula gives us the same answer as we did when we worked out our rise over our run. So let's do the same thing now for MCD. Give ourselves a touch more space. So MCD is going to be the slope, little m means slope, between C and D. So C and D is this little line segment here. So we have the slope between C and D. Well, if we did our rise over our run, what would happen? If we go from C to D, we go 1, 2, 3, 4, 5, 6 of a run across, and 1, 2, 3 up. So our rise would be 3 when we run across by 6. We have a common factor of 3, so we end up with a slope again of a half. We have divide above and below by 3, or take out a common factor of 3 top and bottom, and we end up with a slope of a half. If we did our coordinate method again, so C is going to be at in the door minus 1, up the stairs 1, minus 1, 1. D is at start at the origin, in the door 5, up the stairs 4. That's my x1, y1, x2, y2. So if I write down my formula, always write down the formula and your coordinates and label them before we use this, because as time goes on, this will get really quite complicated. We'll have lots of lines to deal with, and it's important we develop the right structures so that we don't run into problems later. So we sub in, y2 is 4 minus y1 is 1, x2 minus 1, and this hopefully gives an indication as to why we put everything in brackets. If we just said, well, it was going to be minus 1, there's a very good chance we'd make a sign error here, but because we're putting everything in brackets, we can see that this is going to be minus by minus is going to effectively give us plus 1 on this bottom line. So we end up with 3 all over 6, which we know simplifies to our half. Now, if we have a line like our green line for L, so now we're looking at the slope of the line L. So we don't have 2 letters here, we just have 1. So the slope of little letter L. So this isn't a capital L, this is a little letter, or L, which is often what we use for just using a single letter to indicate a line or to label a line. So our green line here, L, we don't have points on this line like we did for A, B, C, and D. So what we can do is simply look for where this line crosses the grid lines and just pick those as being our points. So I can see it doesn't cross the grid line here, so I wouldn't use that point. It wouldn't be a convenient one to pick. I couldn't figure out exactly what the coordinates were. But here, it nicely crosses the grid line. And here, it nicely crosses the grid line. And you can see that it crosses in lots of different places. But what would be my coordinates of my point here? Well, I've gone in the door 3, up the stairs 11. And for my second point, I've gone in the door 6, up the stairs 10. In the door 6, up the stairs 10. So I can use that with my formula to get my slope, or I can use my, once I've picked my points here, I can also use rise over run. If I run across by 3, I drop by 1. So that means rise over run is going to give me that I rise by -1. So I rise by -1. I have dropped by 1 when I run across by 3. So my slope is just -1/3. And I can sub into my formula as well. And when I write down my points, label them x1, y1, x2, y2, write down my formula, sub everything in brackets, it simplifies down to -1/3, just the same. mk is going to be the slope of the line k. And again, I can read this off of the graph by looking at where the line crosses the grid lines conveniently. So I can go for, say, this point here, 1, 7, and the next place I can see that it crosses the grid lines would be at 2, 5. And I could go down further. I could also go down to the point 4, 1. It would work out exactly the same when I worked out the slope. But if we just do this one visually, if we run across by 1, we drop by 2. Well, rise over 1 would dictate that means that my slope is -2/1. Or if we did it using our 4, 1 here, that means that we would run across by 3 and we would drop by 1, 2, 3, 4, 5, 6. So you could have also gotten that you dropped by 6 when you ran across by 3, which would end up simplifying to the same thing. So it doesn't matter whether our points are dead close to each other, our fractions will just simplify to give us the same slope anyway. Now, the last concepts we need to link into this are the idea of parallel lines and perpendicular lines. Parallel, anytime we hear that word from now on, we're going to say that's talking about the slopes of lines, and that means that the slopes of the lines are the same. So if we have parallel lines, we have the same slope. And mathematically, the slope of the first one is equal to the slope of the second one. Perpendicular is where we have our lines at 90 degrees to each other or right angles to each other. And that means it's a little bit more complicated to work out. If we multiply the two slopes together, we get the number -1, or the first slope is the negative reciprocal of the second slope. That means we change the sign and turn the fraction upside down. And that'll give us the slope of the perpendicular. So the symbols for perpendicular and parallel are here. So this means perpendicular and this means parallel. And I'll write that in. So our upside down t-square is our symbol for perpendicular. And our two lines sitting parallel to each other, vertical lines sitting parallel to each other, mean parallel. So those are our two symbols that we'll see often. So is K perpendicular to CD? Let's take our two slopes and see if we multiply them together to get -1. So the slope of K is going to be -2, the slope of, or -2/1, and the slope of CD is 1/2. We already worked them out. If we multiply those two together, we get -1. And that is the way we know we have perpendicular slopes. Now, is CD parallel to AB? Well, parallel means are the slopes equal? And we see 1/2 is equal to 1/2, so they are parallel. And that is what we need for now.